Hello, folks. Welcome back. We're on section 14.5. This is the multivariable chain rule. Let's go ahead and get started, folks. So, suppose we have an experimental high altitude aircraft and it moves along this trajectory here. And that the atmospheric pressure at any point along this trajectory is given by this function in kilopascals. Now, this function looks complicated, but if you look closer, the x only appears one time in the function, the y only appears one time in the function, and the z only appears one time in the function. And so these partial derivatives with respect to x, with respect to y, with respect to z are relatively uncomplicated to work out, because when we're working each of these partial derivatives out, we treat the other variables as if they were constants. And so this is just, for example, the derivative with respect to z is just a constant times e to a function of z. And that's not too bad. These actually are not hard partial derivatives to work out. But what if instead we wanted the rate of change in pressure with respect to time? That is, we wanted to find the derivative of p with respect to t. Then when I start substituting the formulas xt and yt and zt into this function, then I have a function that's got t in all sorts of different places. And then it's a little bit trickier to take the derivative, because then I have to think about the product rule and the quotient rule for this fraction here. And I have a risk of making a mistake. It's going to be a lot harder to take this derivative than it was to take these partial derivatives on this slide. And so what we want to do today is talk about a shortcut that gives us a simpler way of calculating dp dt. It's called the multivariable chain rule. And we'll work through some examples and try to make this work. Okay? So let's look at our first example. Let's suppose that we have a function z equals f of x comma y, and it's a function of two variables. And I'm representing in this diagram by saying that in order to calculate what z is, we need to know what x is and we need to know what y is. That is, there are two arrows coming from z. And then we also have that x is a function of time and y is a function of time. X and y are both functions of t. So to compute what x is, I need to know what t is. And to compute y, I need to know what t is. So what we call this is a dependency diagram. And this is a pretty common situation where we have a multivariable function, but the components of the function itself are time dependent. Then the way that we calculate the partial derivative is we take the derivative of z with respect to time is we calculate the derivative along all four arrows. So along this arrow, we're going to calculate the derivative of z with respect to x. And then along this arrow down here, we're going to calculate the derivative with respect to y. Then along this arrow up here, we're going to calculate the derivative of x with respect to t. And down here, we're going to calculate the derivative of x with respect to t, or y with respect to t. Now, I'm using different notation here because x and y are single variable functions and z is a multivariable function. And so if it looks like I'm doing something funny by using one symbol over here and one symbol over here, this is the symbol for an ordinary single variable derivative, and this is the symbol for a partial derivative. The notation is not important here. We work out all four derivatives, and then what we're going to do is we're going to multiply the derivatives that are along a single path from z to t. So dz dx and dx dt are along one path, and the dx's cancel. And then dz dy and dy dt are on a different path, and the dy's cancel. And both of these leave me partial derivatives of z with respect to t. When we add them together, we get the entire derivative dz dt. Okay? So that's the idea. Multiply along a path and then add the paths together. If this looks like a dot product to you, that's excellent thinking. It is a dot product, and we'll talk about how this connects to dot products later on. Okay? So here's an example. Z is the function x squared y squared plus 3y squared. X is cosine of 3t, y is equal to e to the 4t minus 5. How do we find dz dt? Okay? So we have this dependency diagram where we have z depending on x and y, and then x and y depending on t. I'll fill in the letters in just a moment. So z depends on x, z depends on y, and x and y both depend on t. What we're going to do is work out derivatives along each arrow. So derivative from z to x is 2x y squared, and then this term goes away. So this derivative is 2x y squared. The derivative of x with respect to t is derivative cosine is negative sine, and then the 3 comes out. Then the derivative of z with respect to y, this is 2y times x squared, or 2x squared y, plus 6y. And the derivative of y with respect to t is 4e raised to the 4t minus 5. And then what we're going to do is we're going to multiply along the paths 2x y squared times negative 3 sine t, or sine 3t, and then add the paths together. So that's the first path from z to t, and then this is the bottom path from z to t, 2x squared y plus 6y times 4e raised to the 4t minus 5. And this answer is correct, but sometimes you want your answer entirely in terms of t, and so we have to just make substitutions for all the variables. This answer is going to be very long, but I'll go ahead and write it out. 2 times the cosine of 3t times e to the 4t minus 5 squared times negative 3 sine 3t. So I've taken this expression here, substituted for x and substituted for y. Then I'm going to go over here and do the same thing. Substitute for x. So this becomes cosine squared of 3t times y, e to the 4t minus 5, plus 6y times the derivative 4e raised to the 4t minus 5. And this is also correct and entirely in terms of t. Usually it will be clear whether you have to go through and expand all of this out or not. In general, I will be happy with an answer like this. And WebAssign will sometimes be happy with an answer like that. Okay? All right, let's move on to the next example. In this example, the pressure and the volume and the temperature of a mole of an ideal gas are related by this equation. P times V equals 8.31 is our particular value for NR in this case. And then we have a temperature T. Find the rate at which the pressure is changing when the temperature is 300 kelvins and increasing at the rate of 0.1 kelvins per second, and the volume is 100 liters and increasing at the rate of 0.2 liters per second. Okay? So we want to find the rate at which the pressure is changing. And so that's what we want, is the rate of change over time. And what we have are the rate of change in temperature with respect to time and the rate of change with volume with respect to time. Okay? So we have this dependency diagram where pressure depends on volume and temperature. I put the letters in first this time. And then volume and temperature depend on time. So pressure depends on volume and temperature depend on time. And I'm going to go ahead and remind myself that pressure is the thing we're calculating. So I'm going to rewrite this equation as P equals 8.31 T divided by V. All right. So what we're going to do now is take the derivative along each of the arrows. The derivative of pressure with respect to volume. Volume is down here in the denominator. So that's PV, that's a V to the negative 1 power. And so we get negative 8.31 T times V to the negative 2 over V squared. And then pressure with respect to time, that's just 8.31 over V. And then the derivative of volume with respect to time is 0.2. That's what we're told here. The volume is increasing at the rate of 0.2 liters per second. And the rate of temperature with respect to time is 0.1. All right. And so the rate of change in pressure with respect to temperature, we multiply along each path. Okay. Add the paths together. And then we can go ahead and calculate this out by making substitutions for T and V. T is 300 kelvins, so 8.31 times 300 kelvins divided by V squared, which is 100 squared plus 8.31 over 100 times 0.1. And our answer will be in kilopascals per second. And this is just a calculation problem from this point on. Okay? All right. So that's the idea behind the multivariable chain rule, is we work out the individual partial derivatives, and we never have to work out the entire complicated function. So here's another example. In this case, z is still a function of two variables, but instead of being time dependent, x and y are dependent on time and on some other parameter, like pressure or temperature or charge or something else like that. So z depends on x and y, x depends on t and then this other quantity s, and y depends on t and this other quantity s. So if I want to find the rate of change of z with respect to s, I look at the paths that start at z and end at s, and I multiply along those paths zx and xs, so that's the derivative of z with respect to x, and the derivative of x with respect to s, and then the derivative of z with respect to y, and the derivative of y with respect to s. And then if I want to find the rate of change with z with respect to time, that's zx derivative of z with respect to x times the derivative of x with respect to t, plus the derivative of z with respect to y times the derivative of y with respect to t. The diagram's a little bit different, but the process is exactly the same. We multiply along a path from z to t, and then we add together all the possible paths. So let's try an example of a 2x2 chain rule this way. Okay? So z is dependent on x and y, x is dependent on s and t, y is also dependent on s and t. So here's my diagram. Z is dependent on x and y. And then they're dependent on s and t. And the question is to find both of these partial derivatives. All right, the partial derivative of z with respect to x is, well, the derivative of e to the x is e to the x. So we get e to the x times the sine of y. But the derivative of z with respect to y is e to the x cosine of y. All right. Then the derivative of x with respect to s is, derivative of s is just 1, so we just get t squared. And the derivative of x with respect to t, that's this arrow here, is 2st. The derivative of y with respect to s turns out to also be 2st. And the derivative of y with respect to t is s squared. Okay? So if we want the partial derivative of z with respect to s, we multiply all the paths that go to s. So that would be the derivative of z with respect to x times the derivative of x with respect to s plus the derivative of z with respect to y times the derivative of y with respect to s, which is 2st. And then if we wanted the derivative of z with respect to t, that's the derivative of z with respect to x times the derivative of x with respect to t plus the derivative of z with respect to y times the derivative of y with respect to t. All right. And these are the partial derivatives here. If you need an answer entirely in terms of t, s, and t, you can make the substitutions here. But that's not necessary in most cases. So let's keep going. Here's a more complicated case in which z is dependent on x and y, x is dependent on s and t, y is dependent on s and u, s is dependent on v and w, t is dependent on v and w, and u is dependent on w but not v. So we have all of these different dependencies here. How will we find the derivative of z with respect to v? So in that case, whoops, let's go the other way. To go from z with respect to v, we need to look at all of the different paths that start with z and end with v. And there are three of them. There's one that goes from z to x to s to v. There's one that goes from z to x to t to v. There's not one from z to x to u to v because u doesn't go to v and x doesn't go to u. But we also have the one from z to y up to s and then over to v. Those are all three of the paths that start with z and end in v. And then we're going to take each path and convert it to a bunch of derivatives. And so the path from z to v that goes across the top, z to x to s to v, this is derivative of z with respect to x times the derivative of x with respect to s times the derivative of s with respect to v. And so that's a partial derivative of z with respect to x times x with respect to s times s with respect to v. If we multiply these together, the dx's cancel, the ds's cancel, and we get a partial derivative of z with respect to v, but we have to add that to the other two partial derivatives that we get to get the complete picture of how z is changing with respect to v. And that's what we do on the next slide, is we add up each of those chains that we found. There were three of them, and this gives us the formula for dz dv. This is a long-looking formula, but it's not hard to calculate. So let's try a couple of examples, and we'll wrap up. In this case, u depends on x and y and z, and x, y, and z depend on r, s, and t. And the instructions say to find derivative of u with respect to s at the values 2, 1, and 0. Okay? So let's look at this diagram here. We have u, which depends on x and y and z. And then those depend in turn on r, s, and t. And since right now we're only interested in the paths that go to s, I'm just going to draw those in. And just remember there are other paths along the diagonal, other paths along here as well. But we're not interested in those. Okay? All right. So the derivative of u with respect to x is 4x cubed y. Cubed, let's try that. 4x cubed y. The derivative of u with respect to y is x to the fourth plus 2y z cubed. And the derivative of u with respect to z is 3z squared y squared, or 3y squared z squared. Then the derivative of x with respect to s is r e to the t. Y with respect to s is 2rs e to the negative t. And z with respect to t is r raised to the s power. Z with respect to s is, since this is r raised to the s power, this is r raised to the s times the natural log of r times sine of t. Okay. All right. So let's do some calculating here, because we want to know what this is when r is equal to 2, when s is equal to 1, and when t is equal to 0. So x is equal to 2 times 1 times e to the 0. So x is 2 times 1 times e to the 0, and that's equal to 2. Y is equal to 2 times 1 squared times e to the negative 0, and that's also equal to 2. And z is equal to 2 raised to the 1 power times the sine of 0, and that's equal to 0. And so this expression here, 4x cubed y, is equal to 4 times 2 cubed times 2. That's equal to 64. X to the fourth plus 2yz cubed, this expression is equal to 16. Is there where you can move that a little bit? Maybe not. I was hoping we can move that with the hand, but it doesn't seem to want to move. Okay. And then this last expression down here is equal to 0. Three y squared z squared is equal to 0. And so the partial derivative of u with respect to s, whoops, sorry about that, is 64 times r e to the t plus 16 times 2rs e to the t, e to the negative t, plus, and I'll write the last term in, it's 0 times r raised to the s power, natural log of r, sine of t. And so that's 64 times r is 2 and e to the 0, so 2 e to the 0 is 2, plus 16 times 2 times r is 2 again, times s is 1, times e to the negative 0, that's 4, plus 0. And that adds up to 128 plus 32, 160. All right. Sorry, this diagram got kind of messy. Let's move on. Last example. Z is 3x squared minus y cubed. S is 4s plus sine t. Y is equal to s times t squared. Find the derivative of z with respect to s and the derivative of z with respect to t. Let's see if we can do this without writing out the diagrams and just sort of imagining them in their head. The derivative of z with respect to s is, we're going to look at the change of z with respect to x. That's 6x times the derivative of x with respect to s, and that's just 4. Plus the derivative of z with respect to y, that's negative 3y squared, times the derivative of y with respect to s, that's 1 over t squared. That's it. And then the partial derivative of z with respect to t, we'll take the derivative of z with respect to x, that's still 6x. But this time we're going to multiply it by the derivative of x with respect to t, that's going to be cosine of t, plus derivative of z with respect to y, times the derivative of y with respect to t. That t is in the denominator, so we think of it as a t to negative 2 power. Negative 2 comes down, and then the t to negative 2 becomes t to negative 3. All right, and those are the partial derivatives. Y'all take care. Thanks for putting up with me during these sort of awkward circumstances. I will see you guys on Friday. Y'all take care.